Is it working? So objectives, we want to provide 2 definitions. These were the objectives for the book I was testing last semester. But they're good objectives. Apply 2 definitions for electromagnetic radiation in terms of photon and wavelength. That's something that will be on the you know. Does anybody know that off the top of their head? The definition for electromagnetic radiation in terms of photon and wavelength.
Lambda.
Yeah, that's the thing I'm talking about. So, you know what I'm talking about? Huh? Yeah, that equation. Beer's law. We got a couple beer makers here. What is Beer's law? Huh? Has something to do with making beer?
It's been a while since I've done Chem 1.
Yep. Define photometry, absorbance, percent transmittance, bandwidth, stray light, and linearity. These are all good objectives to know. Determine absorbance from measured percent transmittance. This is one of the calculations you'll have to do. We'll get into the equations for that and how to do that. List components of a spectrometer and provide examples of each component. State the principles of atomic absorption spectrometry and list the substances analyzed by it. Define luminescence, fluorescence, polarization, nephelometry, and turbidometry. Does anybody know any of these?
Turbid is like crap floating around in it.
And what does that do?
It messes up your reading.
No, not there's a specific, there's assays that use turbidometry. So it doesn't mess up your reading. It messes up your absorbance reading if you're trying to measure absorbance of something, but if you're trying to measure the turbidity of a substance, it's not going to mess up your reading. Do you know how it messes up the absorbance reading?
Scatters light?
Yeah, it scatters the light. So it'll show an apparent increase in absorbance when really it's throwing the light off to the sides. So turbidometry and nephelometry are related. They're basically the same thing, they just use a different instrument and they measure the light in a different way. What's fluorescence? Nobody knows? So, don't. Yeah, it's a light that's emitted by a molecule after absorption of light. So, and then luminescence. I know you guys like to go to the parties with the glow sticks and swing them around. That's an example of luminescence. You know, that's chemoluminescence in the glow sticks. So, what do you think luminescence is?
Glowing.
Well, it's light that's emitted from a chemical reaction. It's visible light after a physical or chemical reaction, like in the glow sticks. So you want to list the basic components of a basic fluorometer, state the principle of nephelometry and the principle of turbidometry and the factors that interfere with light scattering measurements. So first off, we'll go photometry. It's the measurement of luminescence intensity of light or the amount of luminescence light falling on a surface from such as a source. Spectrophotometry is the measurement of the intensity of a light at selected wavelengths, and this is what we'll be doing. And this is what a lot of you have done when you're doing protein assays or ELISAs. You're measuring how much light's getting through that sample. So using light for measurements based on the physical characteristics of a sample to absorb light for the most part. Everybody knows light travels as waves. As that frequency gets smaller, what's the energy of that light do?
Goes up.
Yeah. And wavelength. Wait, did I say frequency gets smaller? If the frequency gets smaller, there's less cycles per second. See, I'm tired and mixing my terms up. So if the frequency is smaller, then it's less. It's actually opposite. Your wavelength is longer, right? And the energy is lower. So the distance from the crests of one wave to the crest of the next is the wavelength, right? This is simple stuff. Shorter wavelengths have more energy. White light is polychromatic, meaning it has all the light. Red, orange, yellow, green, blue, and IV.
Indigo, violet.
Black appears if all colors are absorbed. We know that. So wavelength, or is that lambda? Yeah. Distance transverse between, from one complete wave. And that's what this little graph shows. This is lambda. That's your wavelength. Okay. And it's related to the frequency, V, and the velocity, C. So you have this equation here. Frequency, V, equals, what is this typically? Speed of light, yeah, divided by lambda, or the wavelength. So discrete packets of energy, also known as photons, are related to the frequency also, right? So the amount of energy is going to be equal to, what's that? Do you know?
Planck's constant.
Yeah. See, how did you know that?
There's two.
Great. Planck's constant, and then what's that?
Isn't that like velocity? Good question.
And then frequency. Huh? And then also Planck's constant times, what's C? Speed of light or whatever, divided by the wavelength. So that's how, those are all connected together. So big white, so that's polychromatic, right? We're emitting off of there. And it's a mixture of all the radiant energy of different wavelengths. Sun or tungsten filament does the same kind of thing. And you get the whole visible spectrum. You guys have seen this before, right? Radio waves are really low energy. They're about, the wavelength's about the size of buildings. Microwaves are about in between the size of humans and butterflies. A needle point's infrared. The visible light spectrum's here. They're about the size of proteazoans or molecules when you get to UV. And then you get X-rays and gamma rays is really high energy, high frequency. What's that?
He broke his pen.
Oh no. So events that strike, that can occur when light strikes matter. You can get transmission without incidence. So nothing happens, you just go straight through it. Reflection, where it bounces off of it. Scatter, where it's going to be, scattered to one direction or the other. Or you can get absorption. So why do molecules absorb light? Yeah, so. And what happens is you get transition of an electron to a higher energy levels when a molecule is going to absorb light, right? So, and that's what that little thing did. So you have, and you've learned that in general chem. I don't know how to play that again. So it absorbs light, a certain amount of light, where it's going to boost it to a higher state. Okay. Other mechanisms of absorption is you can change the mode of vibration of a molecule's covalent bonds, right? It's another increase in energy of that molecule. Or you can alter the mode of rotation around the covalent bond like that. So, does that make sense? They'll be higher. They're going to be rotating anyways, but you can speed up that rotation or alter it. So a lot of molecules have specific absorption spectra. This happens to be the one, this is from your book, for oxyhemoglobin, right? So you can see there's two peaks at about between 550 and 580 or something like that is where you get peak absorption for oxyhemoglobin. And the fact that some molecules have these peaks where they absorb is going to enable us to quantify how much light is transmitted or absorbed of a particular wavelength, and we'll be able to calculate the concentration of that. So this is spectrophotometry, and it requires the use of a blank. So why do we want to use a blank?
Isn't it to get that? Isn't the reason we do that is so that we can get it to read the right value?
Yeah, so typically your analytes you want to measure are going to be in some sort of solvent, right? Solvents might alter the they're going to absorb light also at the set wavelength that you want to. So basically when you use a blank, you want to make sure all the solvents and reagents are included, but no analyte. So any absorption that the solvent and reagents will absorb won't be included in your analytical sample. So if you subtract that absorbance from the absorbance of the sample with the analyte, you can measure what absorbance is accountable to that analyte, right? Does that make sense? Sort of? I don't know. So transmittance is the amount of light that goes through the sample divided by the amount of light that goes through the blank. Does that make sense? So you get 100% transmittance when they're equal, right? And that's the fraction transmittance. You'd multiply that by 100 to get percent transmittance. So 100% is when the light that goes through the blank is equal to the light that goes through the sample. So absorbance is directly related to concentration, whereas transmittance is negatively related to the log of the concentration. Does that make sense? It's a log linear relationship, not a linear relationship. So as you increase the concentration, your absorbance is going to increase in a linear fashion, whereas transmittance is going to decrease in a nonlinear fashion. Okay? Your machine is set up to basically read the transmittance. You're reading the percent transmittance, and it converts it to absorbance with just mathematically. So, and this figure's not in your book, but it's in one of the other books. I don't know if it's any good. So you have I/O going into the light, and then IS is the amount of that light, the intensity of light that comes out of the sample, that's transmitted after going through the solution. And then this is your reference. This would be perhaps your 0, right? The reference cell. So the radiant energy absorption, IO is the original intensity, IS is the intensity of the transmitted radiant light. And the transmittance is going to be equal to IS divided by IO, right? And that's what we just talked about. Percent transmittance varies inversely and logarithmically with the concentration. And like I just said, the absorbance is directly proportional to the concentration. So when there's a question on the test that asks about this, everybody gets it wrong. Or not everybody, I'd say about 80%. They always say it's, that it's not logarithmically related, but it is. So it drives me crazy. And this is the scale from your book showing you how the two are related. So with 0 absorbance, you get 100% transmittance. And then if you notice, this is a log scale, 0.1, 0.2, 0.3, 0.4, 0.5, 0.6, 0.7, 0.8, 1, and then 2. And then you approach infinity basically to get 0% transmittance, right? So, and that's the table showing you that absorbance is going to be sensitive to pH and ionic strength of solutions too. Why is that? No ideas about why the absorbance might be affected by pH or the ionic strength of the solution? Well, you're going to change the ionic state of the atom, so it'll change the way that molecule, what it can do with the light that it absorbs, right? It'll alter the properties of the covalent bonds. Part of that molecule are the intramolecular forces, I guess? Intramolecular forces. And again, this is the two graphs showing you concentrations, negative logarithmically related to transmittance, and then linearly related to absorbance. And the Beer-Lambert law. So concentration of a substance is directly proportional to the amount of radiant energy absorbed, or inversely proportional to the log of the transmitted energy. And this is the equation. It's a pretty simple equation, right? Big A equals ABC. So where big A is the absorbance, little a is the absorptivity constant, B is the path length, and C is the concentration. There's other variations. I think is A equals ABC in our green book, or did they have a different one?
Same exact thing.
Same exact thing, because what about the math book? I see that's open. That probably has a different one. But it's basically the same thing, they just got different characters for everything, right? You see Beer-Lambert? Yeah.
Epsilon, C,
L. So the one in the math book, it's the same equation, but they just put different characters, so don't get confused. What is it? It's absorbance equals epsilon
CL.
times C times L, where L is the path length, C is the concentration, and epsilon is the absorptivity constant. So same equation, but the books have them with different letters. So long as you remember them both, you're good. So, but it's simple to use. So epsilon's the molar absorptivity constant, and it's used in place of A, and is a constant for a given compound at a given wavelength under specific conditions such as pH and temperature and solvent concentration. Because you're going to have specific conditions in the lab, and you're going to be using those. So the greater the molar absorptivity, the more sensitive the chromogen is for measurements, right? You'll need less of it to get a specific amount of absorption. So, God, I got this one in here multiple times, don't I? So variations from linearity of absorbance versus concentration curve are going to occur when there's very elevated concentrations are measured. The incident radiant energy is not monochromatic. What does that mean? Yeah, well, when you could have leakage coming in, or normally when you're doing this, you want it one wavelength, but it's not all of the machines will just have one. You could have a broad bandwidth, and then you'll be able to, when you're detecting, you're going to detect more than that, so it might not be linear. Solvent absorption significant compared to the solute absorption. You don't want that. Radiant energy is transmitted by other mechanisms. And then the sides of the cells are not parallel, because then you'll get some reflection. And this is going to be, the effect of stray light on true absorbance. So a lot of this, if you get stray light, it's going to throw off your true absorbance. You might end up seeing more absorbance if you have 5% stray light than you would for the true absorbance, right? So simplified spectrometer. So you have some sort of light source, some kind of way to get monochromatic light. You're going to have a cuvette that you'll be shining the light into, and then a transmitted light after it goes through the sample. It's some sort of detector that will be able to have some sort of voltage displayed in the machine that will be able to read out the different, what it's detecting. So these are the basic components of a spectrophotometer. It's a light source, a means to isolate the light to a desired wavelength, fiber optics, cuvettes, a photodetector, and a readout device, a recorder, and a computer. So we all know prisms divide up to the light and all their different wavelengths, right? But typically they don't use prisms, they'll use grading systems. Do you guys have any of those? I think the Florida driver's license has it. Anything with a hologram, if you notice, you can get like the all the colors. Mine is all beat up, so you can't really see it. Do you see a hologram in there? So those are like grading systems where it reflects the light at different angles, and it's another way that a lot of spectrometers are able to break it down into the specific lights. This is what some will look like too, where you can have a reference sample in at the same time, and it automatically will calculate for you the absorbance. Otherwise, what you're used to probably in there for measuring DNA concentrations is you add a blank the machine, and then measure your lights. And this is another one that does it also. This one uses one light source, this one does two. But it goes, so what's the difference between these? This one has a chopper. Oh. And this one doesn't. What would be the advantage of using a machine like this that has a double beam rather than a single beam? What would be the advantage of a system like this over this? Huh?
It has the sample and the reference at the same time.
Yeah, so why is that an advantage?
The person doesn't change them in and out.
Yeah, change them in and out, so there could be errors introduced there, but also the electrical signal isn't always going to be stable, so your light source might not be giving a constant amount of light all the time. But with this, you're using the same exact light source at the same time, so it should be constant. So there should be less variation as far as the light source goes, right? So these are the different sources of visible light. We see the sun gives us a broad spectrum, and then where's the tungsten filament? Oh, this is the tungsten lamp. That's a fairly broad spectrum also, at least in the visible. And then you also have all these LEDs and what first? Mercury vapor lamps and so forth. White LED. So the kind of spectrum you can get. So laser light amplification by stimulated emission of radiation is a device that also uses a light source in spectrophotometry. And this just shows you the wavelengths that you get for the different types of lasers. So wavelength selectors, you're going to use filters sometimes, and that's what our plate readers use. The plate readers we have use filters. So basically you get selective transmission through a filter. We have glass or rattan filters, and it's based on the principle of interference. They're going to interfere with certain wavelengths. Monochromometers is going to use a grading system or a prism. Prisms separate white light into continuous spectrum, whereas diffraction grading is prepared by depositing a thin layer of aluminum copper alloy on the surface of a flat glass plate, and then ruling many small parallel grooves into the metal coating. And this is what is probably more common. That's what you see on it's kind of the similar type setup that you see on the little holograms you see on your cards and stuff. Selected wavelengths is then isolated by mechanical slits. So for filtering, and I guess everything, there's something called bandwidth. What do you think bandwidth means? So this figure shows you something that has a narrow, a wide band pass filter and a narrow band pass filter, right? Versus a sharp cutoff filter. So this is basically the bandwidth. A lot of times you'll get filters that'll give you a rating of the wavelength that you have the peak absorption at, and then which is the transmit where you get the maximum transmittance. I see I reversed this, not absorption, but transmittance, and then a bandwidth around that, basically, which you get M and N. So For wide bandpass filters, they have a wider bandwidth, right? You're going to use those. You're going to have less monochromatic light than you would if you used a narrow bandpass. And then I think it's A is just a sharp cutoff where you're just trying to cut off anything below a certain wavelength. So blanks, transmission of light through a sample is always compared to a blank, and that blank, like we discussed, is going to correct for the absorption of light by materials in the sample other than the analyte. The cuvette's going to absorb a bit, variations in light emission from the source, and power fluctuations, like we said. Variations in the sensitivity of the detector to different wavelengths. So oftentimes you see glass, quartz, and certain types of plastic are transparent to light in the visible range. Quartz is pretty much what you want to use for the UV, although you can buy special plastics that will work for UV. And I think you've seen in the lab we use quartz for the most part, but we do have some plastic ones that can measure really small volumes at the UV range for DNA also. But for the most part, plastic absorbs all the UV. Paired cuvettes are used for a blank and the sample that's the most accurate, and you want to watch for scratches, dirt, anything that's going to interfere with the light transmission through the cuvette. And you also want to check the alignment in the spectrometer and consider disposables for assays that use dyes. Why do you want to do that? Yeah, you'll just end up with some dye on the cuvette. So this is, I think, a figure from your book showing you the cuvette material. Quartz glass, you get good transmission all the way through, all the way down to about 180 or so nanometers, whereas special optical glass is above 300, and then polyacrylate plastic is around the same as the special optical glass. Types of detectors include photomultiplier tubes, photodiodes, charge-coupled devices, and others. But photodiodes are basically semiconductors that change their charged voltage upon being struck by light. And charged coupled devices is a solid phase device that are made of small silicon cells. So when light impinges upon the silicon surface, the electrons are released. And that release of the electrons can then be measured as a current. So they're captured and then quantified because it'll alter the current. Samples have to be well mixed and homogeneous. You can't have bubbles. What are bubbles going to do in your sample? Scatter, yeah, they'll scatter the light. So, and the same thing with particulates. They'll scatter the light also. Solvents for absorption at assay wavelength, you want to use spectrograde if possible, and the absorption varies depending on the pH, purity, and the calibration of the instrument. So, quality control and performance verification. So, calibration, you want to make sure the wavelength is accurate. And then you also want to make photometric accuracy also. You want to see linearity of response. If you see outside a linear response, that could mean you have stray light making its way into the detector, or that you could have noise, electronic noise. Baseline stability and resolution also. That's what we were just having issues with, is our baseline on the HPLC. So calibration should be part of routine maintenance. Wavelength accuracy is the agreement between the wavelength selected and the actual wavelength. Photometric accuracy is the extent to which the measured absorbance or transmittance values agrees with the value of an accepted reference standard. So again, you're going to need standards from this that are traceable to NIST. So linearity of the response, the ability of the spectrometer to yield a linear relationship between light hitting the detector and the detector's response. If that fails, then it'll fail if there's stray light, detector amplifier problems, or a wide exit slit. So stray light can reach the detector without interacting with the sample, right? And that's why it's a problem. It's going to result in erroneous transmittance values. Scratches, dust, fingerprints will deflect the light. And then leaking room light into the sample chamber also can be a source of stray light. And it limits the accuracy with high absorbance values, right? You really should have a lower absorbance value. Noise are going to be short-term spikes, problematic at low concentrations of the analyte, because then if you have a lot of noise at low concentrations of the analyte, you can't, it'll, be hard to detect when you have an analyte there, because you'll be getting a signal, but it could be noise. You guys have heard of signal to noise ratio before? So, what does that mean, signal to noise ratio? So I'm getting ahead of myself because I think I discussed this more in the next chapter. It's on the next test, but everybody gets this backwards. So typically on some kind of spectrogram, there's going to be noise no matter what, and then you'll signal. So the signal to noise ratio, you can just write it as a fraction like that. So if you increase the noise, that lowers your signal to noise ratio, right? Which will make things harder to detect. Whereas if you increase the signal, that increases the signal to noise ratio, makes it easier to detect. So there's always some sort of noise, and that's just inherent in the machine or the room or the building. So the resolution, if the instrument's, it's a property of the instrument, better with more expensive ones, you get, of course. Individual peaks can be distinguished from one another. Monochromometer instruments are better than filters. And why is that? Because with the filters, you're getting, a broad range depending on that band pass. You're not just getting monochromatic light. Checks with reference materials that have peaks close together, such as holmium oxide filters, or how they distinguish the resolution. Performance specifications. Spec choice depends on application. Samples determine special features. Microvolume cuvette systems, software capabilities, ease of operation, temperature controlled sample chamber, and scanning speed. Blah, blah, blah. So qualitative operations, you can use spectral features of a sample to obtain information about the nature of the sample's components. Infrared spectra of organic compounds have distinctive fingerprints. Did you guys do that in organic, or you run an IR spectrum? Or analyze IR spectrum? Yeah, I don't think you run them. I don't think we have an IR. Yeah, they're no fun, are they? Huh? Yeah, well.
Yeah, you get the printouts and then you have to tell the structure.
Yeah.
Tell the structure of the molecule.
Yeah, that's what. So UV spectra is used to confirm drug identity or structural characteristics of a drug typically. But this goes all over the place. Didn't we already do Beer's law? A couple of times? So, but this is important that it's basically it's reduced by three things, right? Concentration of absorbing substance. So why is the absorbance reduced as you increase the concentration?
There's more stuff in there.
Yeah, there's more stuff in there, so you're more likely a photon will hit a molecule in the right way that that molecule will absorb the energy, right? The distance the light travels through the sample, or that's the path length. So why does that reduce the light transmittance or increase the absorbance? Why would a longer path length increase the absorbance?
Less energy.
It's not less energy. So if you have a path length with a certain concentration of molecules, right? The concentration in these two are the same, but if you have a longer path length, the chances, as the light's flying through the sample are increased the longer it spends in that sample. It's like increases the likelihood that it'll absorb, it'll hit the molecule in the right way. And the probability that a photon of a particular wavelength will be absorbed by the specific material in the sample. So this increases the probability that it will be absorbed, and so does this. Both of those together, right? Does that make sense? So determining the concentration, first thing you want to do, you can conduct a standard curve. These are all three ways you can do it. You can construct a standard curve, and when I do the lab, you guys are going to construct standard curves for two different compounds. Okay? And then based on the curve from a previous analysis, if you're in a lab and you have a curve from a previous analysis, you can do that. Hopefully things aren't too far different. Or just based on the absorptivity constant with the reagents that you guys use. So quantitative applications for standard curves, we know this, right? You use known amounts, measure the absorbance for those, and you can graph a curve on the, analyte concentration on the X versus the absorbance on the Y, standards of known concentration, the absorbances determined at a specific wavelength and results are graphed. And given a specific absorbance can determine the concentration of an unknown sample. So we have an unknown absorbance and we can track back to see that. So, and what you guys will see when we do the lab is, hopefully if it works the way it did last year, you'll have your known concentrations. This is your ABS. And you'll be given a series of standards, and it'll look something like that. Okay? So we know, right, that we just learned that the concentration should look like this, right? It should be linearly related to the absorbance. But when we do the graph, we might see something like that. So why would we see something like this rather than that? Do you think? Overlap? Well, it has to do with the ability of the spectrometer that we're using. So when we get to this area of the curve, we're already like at the maximum amount that the machine can detect for absorbances, right? Does that make sense? So when we do the graph write-up or the write-up for the lab, you don't want to include points that aren't linear, part of the linear when you're coming up, with your graph to try to calculate the absorptivity constant and also calculate the concentrations of the unknowns in the lab that we'll do. Does that make sense? So you'll get your data and then go home to do the write-up, plot it up in Excel. It'll probably look something like this, but you want to leave any points out of the analysis that aren't in the linear range of the assay. Does that make sense? And hopefully the unknown will be in the linear range. So, and that way you could, if your single standard is in the linear range, you should have no problem using that to calculate an absorptivity constant and then measure the concentration of that, right? Does that make sense? So that's another way. And some of the problems that you'll see a single standard. You have one standard with unknown concentration, and you get the absorbance for that. You go back to Beer's law, and then you get your unknown absorbance. So you know this one. Get the unknown absorbance. So you can use this and just solve for concentration. We know this. This is concentration K. This is absorbance of K. This is absorbance of unknown. And we can just use this to solve for C, right? If we divide this by that, Do you see how you do that? You don't know what I'm doing, do you? So we have our one standard, we can measure the absorbance of the unknown. The A's will cancel out, so will the B's. The only thing that's left is the C's. This is a number, and that's a number. So if we cross multiply, you get the concentration of the unknown is going to be equal to the concentration of the standard divided by the absorbance of the standard times the absorbance of the unknown, right? Do you see how that works? So they're pretty simple calculations if you just practice them a couple times. I think in the math book has some practice problems, and all in all they're really simple. The math book also has those practice problems where you're using a standard, and it will have graphs that look like this also, and then you have to, determine concentrations of unknown, and remember to eliminate parts of the graph that aren't linear. Does that make sense? So, using previous analysis to determine common concentration, sample calibration curve used for all samples. The instrument has to remain calibrated. Solvents and reagents have to be consistent. Assay conditions have to be consistent. If the air conditioner is broken when you did the first time, it must be broken the second time too, because the temperature is going to affect absorbance. Proper blank has to be used for both when constructing the standard curve and when measuring the absorbance of the samples. So the absorptivity basically is going to govern the steepness of this standard curve, right? And it's dictated by the nature of the standard, how that absorbs light, and the path length. Remember, the longer the path light, the more opportunities those photons have of striking the analyte of interest of the standard. There's an inherent tendency of a material to absorb light at a particular wavelength. That's called the absorptivity, and the value of the absorptivity is constant of a particular compound at a particular wavelength, and that's called the absorptivity constant. And determining concentration based on absorptivity constant is easy. If you know the absorptivity constant, then you just plug it in. Your unknown absorbance is going to be equal to, the absorptivity constant times the path length, and then times the concentration. So concentration is going to be equal to, unknown concentration would be equal to the absorbance of the unknown divided by absorptivity constant times the path length, or you could have A and B down here too. So depending on which letters you prefer. What letters do you guys prefer?
Whichever comes on the test.
Huh?
Whichever comes on the test.
Yeah.
B.
You like A, B?
Or X, Y.
Not epsilon, L?
No, I don't like those.
Is it problematic if they just left the HPLC down?
So long as it doesn't run out. Well, it's running on methanol. So look at that first bottle. Methanol, 20% methanol. You could slow the flow down by just typing it in there to like 0.01.
Okay.
Huh?
Slow your roll.
Huh?
Slow your roll.
So if the absorptivity constant is from the literature, constants can only be used to give estimators a concentration. To know how much of an analyte is actually in a sample, you have to construct a standard curve. So when we measure DNA samples, it's all from the literature basically, so we're estimating your DNA concentrations. Deviations from Beer's law. Stray light causes nonlinear response at high absorbances. Didn't we already do this slide? What?
I think so.
Yeah, low levels of absorbance might be inaccurate due to noise in this system, and outside the linear range of the assay system, that's when we're going to be up here. Does that make sense? So So colorimetric assays, that's the ELISA you guys did, and the protein assay if you took proteins class. Those are colorimetric assays. You probably do a lot of colorimetric assays? No?
People on day shift might, but we don't on our shift.
No? Okay. Not 96 volt plates where they change color. So specs that can only analyze materials that absorb light, and anytime you see a solution with the color, that means there's something in there absorbing visible light, right? And this substance is exposed to the reagents and the conditions which the compounds so it can be measured. So we use colorimetric assays to give color to something that we normally did, like ELISAs. You handle standard samples and blanks identically, dilute the samples outside the assay's linear range. Fluorescence assays are governed by this equation, so you get the relative fluorescence intensity is going to be equal to the fluorescence efficiency, which is the ratio between the quanta of light emitted and the quanta of light absorbed. And that's equal to the initial excitation intensity times the molar absorptivity times the volume element defined by the geometry of the excitation and emission slits, and then C is the concentration in moles per liter. So why would the absorptivity constant be effective here in fluorescence? Why would it be part of this equation? What do you think? Yeah. You only get fluorescence if the molecule absorbs, right? So with fluorescence, you get a molecule is going to absorb light, boost an electron, and then when it drops back down, it emits light, right? When it returns to its ground state, you get that light emitted. So that's why you include the absorbance, or the molar absorptivity, because the amount of light that's going to be absorbed. This is the excitation intensity, which is going to totally do with how much light gets absorbed, right? And then the fluorescence efficiency is the ratio between the quanta of light emitted and the quanta of light absorbed, and that has to do with the difference between those two. So you'll see the amount that's fluorescence. So fluorescence measurements, they're going to be linearly related to your concentration, like this. So your fluorescence, the amount of fluorescence should increase in a linear manner based on concentration. Does that make sense? So, I think that's... Have anybody ever heard of fluorescence polarization? So we know light's composed of electrical and magnetic waves that are at right angles to each other. So they're going to have some kind of geometry to them. So when typically light sources generate these electrical vectors oriented randomly, so they're oriented in every which way, right? But you guys have seen those blue blocker sunglasses? I don't know, I remember seeing commercials for those when I was young. They're like sunglasses that block the blue light, make you see, so you don't get reflection off a pond, so you can see where the big fish are. You don't remember those commercials? Huh? They're basically polarizing filters, so they polarize the light. So, and what polarizers do, they'll only allow light that's in one orientation to flow through it, okay? So, I need to get some polarized filters so you just twist them around. You can change the amount and intensity of the light that goes through. If you have one polarization filter here, one here, you'll get all the light going through and then when it comes out, it'll be polarized in one direction. And as you move them, you get less and less light. It's kind of neat. Anyways, so polarizers, they'll orient the light into a single plane, and they're going to be plane polarized at that point. Fluorophores are going to absorb light most efficiently in the plane of their electromagnetic energy levels. So if the light that's polarized strikes the light of the fluorophores in the same, you'll get the maximum intensity from those fluorophores if they're perfectly aligned. But fluorophores rotate, right? Or molecules generally have rotation, Brownian motion, where they're constantly spinning. So you'll only get a certain population of those fluorophores excited with one plane of light, and then they'll turn and emit their the fluorescence polarized light afterwards. And because small molecules have rotational relaxation times that are much shorter than their fluorescence decay time, their emitted fluorescent light is depolarized. However, small fluorescent molecules are attached to a macromolecule, so it's a big molecule. Does that make sense? Small molecules spin faster than large molecules. So large molecules placed in or if it's placed in a viscous solution, anything you can do to slow the rotation down, that small molecule will then emit polarized light. So if they fluoresce, polarize, and then they rotate, they're going to emit light that's not polarized because they're spinning so fast. But if they're attached to a large molecule, it'll be polarized, so you can measure that as polarized light coming out, fluorescence. Why do you think that's important for clinical assays? What do we use a lot of times in clinical assays to detect analytes? That's a big molecule. I know you guys know this. Think of big molecules that are used in clinical assays all the time. Who here is taking proteins?
What?
Huh? It's a protein. Proteins are typically big. What?
Albumin.
Not albumin. Although I guess you could use albumin, but the antibodies. So that's even bigger than albumin. They're about 134 Daltons, 134,000 Daltons. Yeah, right? So antibodies, they're going to spin slowly in solution. So you can use antibodies to detect small molecules. And this is fluorescence polarization assay, and that's how that works. So you use an excitation source to excite the light. Goes through a polarization filter, so you only get light that's polarized. If it binds to a fluorophore that's bound to a large molecule, it'll emit polarized light. At the detector end, you have polarization emission. You can detect that. You don't get any emission through the filter that's opposite the polar. This is going to filter that out because that polarization filter is opposite direction. You'll be able to detect this. So you can tell you have polarized emission. If the fluorophore is linked to a small molecule, it has faster motion, and the emitted light is depolarized because it's going to be spinning fast, and it'll depolarize the light, and you'll be able to detect that there's depolarized emission there. Right? So this is the basis for one of the assays that we see. It's called fluorescence polarization immunoassay. So the immuno is they're using antibodies. And it's for detecting small molecules, and it's a competition assay where they've attached a fluorophore to the small molecule you're interested. So you have fluorescent analyte there that's going to compete versus the analyte that's not labeled in the sample. And you get when you have less analyte in the sample, there's going to be more large antibodies that are labeled with the fluorophore, because this is one of your reagents, is that small molecule labeled with the fluorescent analyte. Whereas if you have lots of analyte in the sample, it'll outcompete the fluorescently labeled reagent, and then you'll get depolarized emission rather than polarized emission. Does that make sense? So we'll get into that in one of the later chapters. And this is typically a schematic diagram of fluorescence polarization analyzer. So you have the excitation going through a polarizer, and then you measure the light, the fluorescence light emitted at 90-degree angles. That goes through another polarization filter and then through a detector. So, polarization analyzer, rather. Turbidometric assays. So turbid solutions contain suspended particles that both absorb and scatter light. The shorter wavelengths are scattered more easily than the longer ones, and inconsistencies affect absorbance readings. So absorbance and concentration of organisms have a linear relationship. So again, back in that proteins class, you grew yeast over a time period, and you used the spectrophotometer at, what was it, 600 around there? And that's basically just looking at the scatter of that light, not the real absorbance, and you measure basically the population of the yeast as you're going along. So Rayleigh's light scattering equation is this, so that intensity is scattered light divided by the intensity of excitation light, and it's equal to that 16 pi a sine squared 2 theta. The angle of observation divided by the wavelength of the incident light divided by the square of the distance from the light scattering to the detector. And the concentrations and molecular weight factors are going to affect the scattering of light. So don't worry, I'm not going to include these on the test, I don't think. These were from that other book anyway. I forgot there was all these equations in that other book. But turbidity measurements are like this. So turbidity is going to be equal to this little t. And b is the path length of the incident light through the solution. So again, increase the path length is going to increase the amount that gets scattered. I is the intensity of the transmitted light, and IO is the intensity of the incident light. And these are typically what turbometry is typically, you measure it with a 0%. You just measure, basically you can use regular spectrophotometers to measure the turbidity, and you're looking at basically how much incident light is reduced. Whereas this is the important thing to know, is nephelometry, instead of using a normal spectrophotometer, you're measuring the incident light typically at 90-degree angles, but there's some that have forward scattering nephelometry at 30 degrees. So rather than measuring the reduced amount of light that's going through the sample, you're measuring the increased amount of light at a certain angle from the sample. Does that make sense? So the more you have of particles in nephelometry, the higher your signal would be, and the lower the signal would be if you were measuring it via turbidometry. So just remember that they're both opposite in what direction that they go into. Okay? So if you have a turbid sample, less light will pass through it, but you'll be able to detect more light at a 90-degree angle. Does that make sense? With nephelometry, you're measuring the light at a 90-degree angle, and the more particles in that solution, the more intense the light that's scattered off to the 90-degree angle is that you'll be measuring. Does that make sense? So I guess that's it for this chapter, I think.